we are talking about differentiation in calculus. The most basic thing in mathematics is addition. Anything, subtraction, multiplication, division, calculus, logarithmic, exponential, whatsoever. It's kind of the bigger form of the, or different form of the addition. So mathematics starts from addition. We add two items, 5 items. So, okay, so let's proceed on integration, the concept, basic concept of integration. Then we'll come to differentiation. Okay, so I add 7 orange per day. I get 7 orange per day. What about after T days? How much orange I collect? 7 into T. Every day 7. 7 plus 7 plus 7 plus 7. If it is 10 days, it is 70. If it is T days, 7 into 2. So first is addition, 7 plus 7 plus 7, 10 times. Bigger addition comes to multiplication. So rather than 7 plus 7 plus 7, 10 times, 7 into 10. After T days, 7 into T. So the beginning of the mathematics is addition. Bigger addition is multiplication. Okay. There is one form of addition is multiplication. Another form of addition is calculating the area. Like if I add 7 orange every day, and at the end of 10 days, 7 orange every day, at the end of 10 days, it comes to a rectangle. The x-axis is days and y-axis is how many oranges I collect. At the end of 10 days means it becomes a rectangle. If I calculate the area of the rectangle, that becomes 7 into 10. So addition, if we simply keep on adding, better addition is multiplication. 7 into 10. Another form of addition is calculating the area. That is integration. Integration is nothing but a form of addition where we calculate the net amount at the end of a time period by calculating the area. So we draw a shape based upon the two axes and we come to a shape, and net collection is area of the shape. So if I am collecting 7 orange every day, at the end of T days, the rectangle has area of 70. Okay, so that is the integration. First day, I collect 1 orange. Second day, I collect 2 orange. Third day, I collect 3 orange. So at the end of third day, I have 6 orange. 1, 2, 3. At the end of T day, on the 10th day, I collect T orange. How many oranges I have collected? Addition failed, means 1 plus 2 plus 3 plus 4 plus 5. Anyone would kind of surrender. And multiplication failed because it is not linear. So we come to calculating the area. Now it becomes a triangle. Day 1, 0 means 0, then 1, 2, 3. So it keeps on growing, it's a slope, and it becomes a triangle. So at the end of T days, the total collection is the area of the triangle. That is T square by 2. So that is the area of the triangle. Okay. So 1, 2, 3, 4. If I first day, if I get 7 and Next day I get 14, third day I get 21. It comes to same thing, 7 into. So it will become 7 into, so 7, 14, so 7 if I take, then it will become 1, 2, 3, 4, 5, 6. So it will be kind of 70 square by 2. Okay, so I mean, just we calculate the area of it. Okay, so small addition, bigger addition, multiplication, non-linear addition is area. We calculate the area and we get the how much we collect. Okay, what about reverse? At the end of t days, I collect t square by 2. Then, how much I am collecting any day x or any day t. Okay, in reverse fashion, we can say what is the speed. If I have the net amount collected, I know, then what was the collection on a particular day? At the end of t days, I am able to collect t square by 2, total amount. Then any day x, on that day x, what was the collection? Okay, so any day the collection is, in our equation, it's a triangle. So any day collection is t. So first day 1, second day 2, third day 3. So that t I have to get back from the t square by 2. So integration is, if t is the collection per day, then net collection is t square by 2. If net collection is t square by 2, what is the collection per day? That is differentiation. Okay, so basic thing is integration. Obviously, anyone wants to collect the add. No one wants to divide. I mean, multiplication bigger form is, another form is integration. Then differentiation is kind of another form of division. Okay, so if I am collecting 7 oranges every day, at the end of t days, total collection is 70. If total collection is 70 at the end of t days, then how many oranges every day we are adding? So that is differentiation. Okay, from we started per day, that amount we have to get back when we have the net amount. We call it velocity, we call it speed, whatsoever. So if I have the net amount, then what was the speed? What was the velocity? Or how much was the collection? So on a particular day, what was the collection? So that is differentiation. A man is walking. I mean, in another way, we can say collecting distance. Okay. So kind of at the end of first hour, he started from 0, means he was standing. And he is increasing the speed. I mean, whatever he is collecting in 1 hour, next hour the collection will grow. Third hour collection will grow. Fourth hour collection will grow. Okay. So that way we will talk about the integration. Okay. So a man in the first hour collected, he started from the rest. And man collected in first hour, he collected some amount. Second hour, he collected some amount. Third hour, he collected some amount. Okay, so let's suppose the collection is like a sine t. Sine t, at the t equal to 0, he is at rest. And t equal to 1, at that moment, so t equal to 1 means in first hour, he collected some kilometer. T equal to 2 means first, in the second hour, he collected something. T equal to 3, he collected something. Okay, so at the pi by 2, he collects at that interval, he collects 1. That interval. Okay, because sine pi by 2 is 1. Then again he proceeds and sine pi is 0. This means he is growing the collection up till he reaches pi by 2. Then collection of kilometers means he is collecting some kilometers in 1 unit of time, next unit of time, next unit of time. So in the unit of pi by 2, he is collecting 1. Means that is his collection kind of his tendency. Then he is decreasing the collection, and at the pi he stops. What is the total kilometer he collected? I mean, what is the total kilometer he walked? So from 0 he started and sine t. Okay. So if I integrate, if I calculate the area from 0 to becoming 1 and then 1 to 0, that area becomes minus cos t. Okay. So first section from 0 to 90, that is he walked 1 kilometer because cos 0 is 1 and cos 90, cos pi by 2 is 0. So 0 minus 1 minus cos t, that is the integration. So 1 kilometer he walked. In the next section, when he is collecting kilometers less time by time, then cos pi is kind of minus 1 and cos pi by 2 is 0. So minus 1 minus 0 minus 1. So minus 1 minus 1 minus 2 minus cos t. 2 kilometer he walked. So so this is integration. If a person walks collecting kilometers in a fashion the sine wave is, then from 0 to pi, how much he collected? He collected 2 kilometers. From pi to 2 pi, how much he collected? No, it is negative the way we see the sign. Negative means he is coming there. He proceeded with growing the collection of the kilometers. At the one moment, the collection is maximum. Then he decreased the speed, he comes to a rest. Negative sign means he is coming. So from pi to 2 pi, he started coming. So start from the rest. At one moment, the collection is maximum, and then he comes to rest. How much kilometer means how many kilometers he collected. So that is the area, and area is the positive and negative are same. Means he came back to the same point. Okay. So this is integration. Once we calculate the area, then after calculating the area, we come to know that what is the total addition. So integration is nothing but kind of another form of addition or multiplication, whereas differentiation is another form of division. So now here we'll see the differentiation. We saw if someone is collecting oranges, 7 oranges every day, at the end of t days, total oranges he collects is 70. If he collects 70 at the end of t days, then how many oranges he is collecting per day? So that is differentiation. If he is collecting t square by 2 at the end of t days, then how many oranges he is collecting every day, I mean, or any day t, that is t. If someone is collecting kilometers, that is in minus cos t, then how much he is collecting, what is his collection at any time t, that is differentiation. So first is 70, differentiation of 70 is 7. Another is t square by 2, differentiation of t square by 2 is t. Here it is minus cos t, that is the integration of the sine t, we got minus cos t. Differentiation is sine t. So differentiation is nothing but the speed at which the addition is happening. So that is the differentiation. Now differentiation can be meaningful in many ways. Like if a person is working from the rest and at the pi by 2 he is at maximum speed, then at the pi he comes to rest. Again 3 pi by 2 he is at maximum speed. Okay. At the maximum speed, so sin t is the calculation way. So sin 90 is 1. Okay. Sin 270, 3 pi by 2 is minus 1. Now, question arises is, if we see the differentiation, differentiation is what is the speed, means what is the actual collection every moment. Okay. So, the speed at pi by 2, that is the differentiation, that is the minus cos t, is 0. Again 3 pi by 2, cos t is 0. So, if I have the collection curve and if we calculate the differentiation and it becomes 0, this proves that there was a turnaround, there was an arc. Okay, so that is differentiation. The unit through which addition happens, that unit is differentiation. If we know the net addition, from net addition back to the unit, that is differentiation. Okay, so we'll see what is differentiation on the slides. So this is Linux Mint. Okay, so we have kind of a time interval 1, 2, 3. Okay, so we have kind of we have a collection. So this is the first time interval. So width is 1 and height is 7 and more than 7, 7, more than 7. So addition is something like all the bars what we see. So every one, the area is whatever the height is because width is 1. So if we want the total collection, that is the addition. So that will become kind of adding all these bars height, because width is anyway 1, so area would be height by width into width. So this is addition. In multiplication the height should be same, and if you want to multiply for the 5 days it will come to 7 into 5. So this is multiplication. So as we learned that multiplication is nothing but bigger addition. So addition, if we have kind of 7 oranges collected each day, 7, 7, 7 for 5 days, so it will come to 7 into 5. So that is multiplication. Or we can go for addition, 7 plus 7 plus 7 plus 7 plus 7. Or so addition is nothing but kind of adding the these bars, and multiplication is nothing but how many times it is repeating and multiplying by that. So everywhere we are adding only. So there is nothing more than that. Addition is simple addition. Multiplication is kind of more complex, means 7 into 5 what we do. Now we go for integration. Multiplication comes in area also. Like if we see closely, this is a rectangle. So 7 oranges if collected during 5 times, 7 into 5, 7 into 5 leads to the area of the rectangle also. So integration comes into the picture when kind of it is not a smooth, like this is a sine wave. So from here to here it is straightforward, and then it is a sine wave. So if you want the total addition, how much is collected up to t time. So t can be anything, t can be fraction also. So in that fashion, collection if kind of integration is kind of better multiplication is better addition, and integration is better multiplication. Multiplication is also an area of the whatever shape we kind of deduce, and the reduction shape, if it is not smooth, we go for integration, and we purely go for area. So in multiplication we go for multiplication, or we can go for area. In integration we purely go for area. So if I have a kind of collection like this, for some time it is flat and then it is a sine wave, then any time t we have to, if I am able to collect the area, that is the collection. So that is the integration. So that is difference in addition, multiplication and integration. Addition is pure addition. Multiplication is either multiplication or area. Integration is pure area. So we get the added amount by calculating the area. So that is integration. Okay. So like the collection of item is at the time 0 is 0, at the time 1 it is 1, at the time 2 it is 2, at the time t it is t, then how much is total collection at any time t. So that is the area of this triangle, that comes to t square by 2. Now we will move to differentiation. So if we know the area, that is t square by 2, what is the equation of this line? The slant line what we are seeing. What is the equation of the total collection? Okay. Kind of what is the speed? What we discussed. So if we know the area, that is t square by 2, then what is the equation of this line? How much is the collection at any point of t? So if I say t square by 2 is the total collection at the time, during the time t, at any time t, what is the collection? Like any time 1, collection is 1. Any time 2, collection is 2. Any time t, collection t. So that at any time t, what would be the collection? That is called differentiation. Differentiation of the area. Differentiation of the area becomes the t. So differentiation is nothing but finding the t. Okay. So kind of okay, so it is represented as like this. So if I say fx is a function, then integration of fx okay, so kind of integration of fx. Okay, so fx, if fx is a function, then area is integration of fx. Okay, if area is integration of fx, then fx is differentiation of area. Okay, so if we want to get back the fx, then we have to do the differentiation of the area. If fx is a function, so here function is t. So if fx is the function, okay, so if fx is a function, So this is fx, and then area is integration of fx. If we know the area, if we do the differentiation, we get back the fx. So that is the idea. So here the question mark is t. So the equation of this line, slant line, is t. So if we know t square, area is t square. If area is t square, then differentiation is nothing. It is kind of it is denoted as d by dt. So we'll say like okay. So it is dt square by dt okay. So this is differentiation, means how we denote differentiation, that is dt square by dt. If that is the case, then it comes to t, because this is what is the reverse of the integration. So this is concept of differentiation. If we know, okay, so if we know the area, if we know the function, then area, if we want, we have to do integration. If we know the area, then how to get back the function is differentiation. Okay, so that is how it is. Okay, like if a person is walking in a kind of a sine wave, like it starts from 0 and after some time he reaches maximum, that is 1, and then he decelerates and his speed comes back to 0. At any moment x, how many kilometers he has walked, that is the area that we see in green. So if the equation is sine t, so if equation is sine t, then area would be integration of sine t, that is minus cos t. So between x and 0, that would be like minus cos t between x and 0. So this is the area that he walked. So if we know the kind of the equation of this line, then calculating the area is integration. So if we know that person is walking or he is collecting how many kilometers at a particular time, means what is his speed at particular time, how many kilometers he has walked, that is the area, that is integration. If we know how many kilometers he has walked, then what is his speed, that is differentiation. So if I know, so I can write like this. Okay, so I can write like this. D sine, now I know that area covered is minus cos t. So I can say sine t equal to d of minus cos t, by dt. Okay, so this is, so if I know, if the equation of this line is sin t. Okay, then that equation can be brought back by doing the differentiation of the area. Okay, so if I know the area is of this kind of sinusoidal speed is minus cos t, then if I differentiate minus cos t, I'll get back the speed. So that is a sin t. Either I get back the speed, or how many kilometers are collected at any moment, or the equation of the line, whatsoever. So if I know the equation of the line and how many area collected, if I want to know, then I have to do integration. If I know what is the area of the collection, then I want to get back the equation of the line, how many kilometer collected at any moment, and then I have to do differentiation. Differentiation is getting back the equation of line. Okay, so this is the integration and differentiation. Integration is addition, means we get when we calculate the area, means we are actually calculating the collection or addition. Differentiation is division. Okay, if we divide, then we get back the rate. Like if someone is getting 7 orange every day, and after 10 days he is getting 70 oranges. If he is getting 70 oranges is 10 days, what is its rate of getting oranges per day? So that is 70 by 10, that comes to 7. So differentiation is division and integration is addition. Why we cannot do addition or division directly? Because the curve is, there is no smooth line. The line is not smooth, it's not flat, it's a kind of a curve. In that way we cannot go for addition. So we have to calculate the addition only by calculating the area. That is the only way. As we talk, that simple addition we can do one by one. Multiplication is just multiplying the width into height, that becomes area, means knowingly, unknowingly. And if we know that multiplication or bigger addition is area, then we can go by, means purely calculating the area to get the total collection. Okay, so a person is walking, now we'll kind of proceed more on it. So like a person is walking in sine wave, and how much distance he has collected up to pi by 2. So that is integration. So sin t dt and 0 to pi by 2, that comes to 1. So 0 to pi by 2, even though this height is 1, he has collected 1 kilometer. Similarly here also, in this graph, here also it will collect 1 kilometer. So 1 kilometer, 1 kilometer. Up to pi, he collected 2 kilometers. Okay. Then if he proceeds, then sine wave goes into negative direction, means he is coming back. Sine wave is in positive direction, means he is going forward. Sine wave in negative direction means he is coming back. So if I calculate how much he has walked pi to 2 pi, that is minus 2. So here it is 2 and here it is minus 2. So at the end of 2 pi, the total distance he has covered is 0, means he came back to that location again. So this is integration. So if you see the total distance he covered from 0 to 2 pi, then the sin t is the wave, then 0 to 2 pi, if we do the kind of integration, it comes to 0. What is the role of differentiation? So if we know the area at any moment, then if we differentiate, then we get back the equation. If I have the equation and I do the integration, I get the area collected, means the kilometer collected. If I have the kilometer collected and if I differentiate, I get back the equation. Okay, so now we'll see the real scenario. Like I have a kind of a capacitor circuit. There is a voltage source, that is DC, and there is a capacitor. So capacitor is a kind of a battery which stores the charge. Like this is a typical curve that we can see. like as time proceeds. So if I connect a voltage to a capacitor, okay, slowly the voltage across the capacitor would start growing. If voltage across the capacitor start growing, if I multiply by capacitance, I get how much charge it has collected at that time. Okay. So if I know the current, so current would vary. If voltage is varying, current would vary. If current is varying, at the beginning current is different. Time to time current is different. Okay. So if I have a current curve, like at the beginning the current is very high and slowly current is dropping, and after some time current will be zero. It is called capacitor is fully charged. If I know the equation of current, then the total charge that capacitor accumulates is area. Means that is the kind of fundamental, like we can see by many ways. If I know the total charge accumulated in the capacitor at time t, then if I want to know the current at that moment at the time t, then I have to differentiate it. Means if I know the area is, if I draw the current diagram, if I know the area means total charge. If I know the area, then I want to know the current at any moment, that is the equation of the line, then I have to differentiate. Okay, that will prove. Okay, so if I know the voltage at any moment, means I know how much charge it has deposited. So if I know the charge, how much charge it has kind of accumulated, then at that moment, if I want to know the current, then I have to do the differentiation. And if I differentiate dq by dt, and whatever the current I get, so that is kind of a differentiation, that is the differentiation of the area. So if this fundamental is correct, whatever I am thinking is correct, then I, whatever we are calculating through experiment, so I will calculate through experiment, and then voltage anyway kind of, so during the time we'll calculate the I, and we'll calculate the I through the equation. So we'll see. Now this is the one graph that we are seeing. If I know the current, then area is the charge. If I know the charge accumulated, then current is differentiation. Like if I have capacitor is charging, then this curve that is kind of growing, this is the charge. So kind of time to time charge is growing. At one level it would become kind of, it will be completely saturated. So charge won't grow, voltage won't grow. Okay. If I differentiate this dq by dt, then this line differentiation would be current line. So at the beginning current would be high because the slope is high. At this moment the slope, differentiation also find the slope. So at this moment slope is high. Okay. At this moment slope is nothing because it is saturated, so current is zero. Okay, so this will prove, means our fundamental is, if I know the area, then differentiation is the line equation. If I know the line equation, then area is the integration. So right now we'll prove the differentiation. So if I know the Q, when I know the voltage, if I know the voltage, I know the Q. Okay, so I'll differentiate the dq by dt, and I'll find the I theoretically. Okay, so if I know the voltage, then I know the Q. If I differentiate the Q, then I find the I. Once I find the I, that would be kind of theoretical I, what we get through the formula. That will corroborate through the kind of actual fundamentals. So actual circuit. Okay, so now little bit kind of differential equation, mathematics we see. So kind of I have a resistor and a capacitor, current is flowing. So charge accumulated at current is the voltage across the capacitor and the capacitor at any moment. So kind of the voltage across Vs is kind of a source voltage that is equal to the resistor voltage and capacitor voltage. Source voltage is resistor voltage nothing but resistance into the current at that moment, and this is Qt by C, that what we are saying. Okay, now we can kind of current is nothing but dQt by dt, dq by dt, and this is Q by C. This comes to a differential equation slowly. Okay, now further we can see Cv dt equal to Cr dq plus Q dt, dt equal to Cr into dq by Cvs minus Q. So this is the variable Q and this is the differential. So this comes to pure differential equation. Now we are trying to kind of reduce the voltage across a capacitor based upon the time. Theoretical voltage, what we see. So then we'll calculate theoretical current and we'll prove it by practical current. Okay, now this is a differential equation where we have dt and that is dq by Cv minus Qt. If I say Cvs minus Qt equal to u, then dq is minus du. So it comes to like dt equal to Cr into minus du by u. If I integrate, then further we come to like this, and finally we'll come to like the voltage means voltage is variable at any time t equal to Vs, that is fixed, 1 minus exponential time minus Cr. So if I place t any second, calculating this with C and R, that is kind of constant and Vs is constant, I can find Vt, means this is theoretical Vt. If I know the Vt, theoretical Vt, I know the char, then theoretical current I can calculate. This theoretical current will verify with the practical one. So that is the idea. Okay. So if it is the theoretical voltage Vt equal to this, then calculating current is C dB by dt. Okay, and finally we'll come to theoretical current at any moment is 1 by R into Vs e to the power minus TL. Okay, if I draw the graph, then current should be like this kind of. So we have taken kind of okay, so we have taken like capacitance as 220 microfarad and resistor we have connected and it is 56 kilo ohm, and ammeter we have seen voltage is 2.57 volt, and this is the circuit we have kind of connected where ammeter is connected to the voltage source like this, and then capacitance and resistance are connected like this. Okay, now we know the capacitance, we know the resistance, we know the Vs, we know the R. So theoretical current would be like this with our mathematics. So beginning would be around 44 micro ampere, and it would proceed to kind of later, and it would become 1 or 0. So this is the theoretical current that we will calculating. Now we will do the practical. So this is the kind of practical that will see. Okay, so we have taken one multimeter and it's the basic one, and there is one capacitor 220 microfarad, and there is a resistance that is 56 kilo ohms. So that is the scenario. Now we'll check the voltage across the capacitor, and it should not be anything, it should be 0. Okay, so there is some voltage, so we'll shunt it and calculate again, and we'll try again. Okay, so there is no voltage in capacitor, that can be seen, 0.07 volts, so there is nothing. Okay, so we'll connect it. Okay, so we have made the connection. Now it is ammeter based, so we'll place it to ammeter, and it is microampere, and ammeter is connected with the negative of the battery, and positive of the ammeter is connected with the capacitor, and it is as per the diagram. And now the positive of the battery will connect here, and we'll see the measurement in the ammeter. Okay, so it started with 41, and we can see that initially it was very sharp, and current is kind of decreasing. Initially current was 41 microampere. Okay, so we'll leave it. Now the current flow is less slow. Now it is 5 microampere, 4, and now it is even. So this is a kind of exponential curve, where beginning the slope will be higher and at the end slope will be low. So we'll wait it till it reaches 1. Okay, so it reached 1. So this much time it took to charge. So that is the scenario. Now we'll calculate the voltage across the capacitor. We'll disconnect the capacitor all along. So now there is nothing in the capacitor. So we'll measure the voltage across the capacitor. How much it reached? What is the battery voltage? So battery voltage is 2.56 volt, and we'll measure the capacitor voltage, how much it has reached. Okay, 2.4 it reached. It is decreasing, so it would have reached higher than that. Okay, it is 2.28, so it is decreasing. So capacitor is getting discharged. Okay, so with practical we have calculated the reading. So we see at the time of 0, expected is 4.64, means that is the calculated, and whatever we got there is nothing. At 0.33 second it shows 41 microampere, 1.06 second 39, 1.36 38, 1.73 37, 3.46, and at 15.56 second the current is 12 microampere. So this is what we are getting in the practical sense that we have seen, and at the end of 59.5 second the current well reaches 1 microampere. This is what we saw in the current video. Now the voltage what we have taken into consideration is Vs is 2.57 and initial voltage of the capacitor is 0.707 volt. So for kind of maximum accuracy we have taken the voltage source as 2.5 volt, and then we have calculated the theoretical I based upon this equation, and that is the left one. This is the theoretical I what we expect based upon the equation. This is the practical I what we are getting. So theoretical is 43.4, practical is 1. Theoretical is 33.71 at the time 3.46 seconds. Practical is 32. 7.5 second. Then theoretical is 24.28 microampere, whereas we are getting 22. So it's pretty well. I mean, there can be internal resistance to capacitance also that we are not measuring. Resistance may not be 56 kilo ohm as per it is written, and so this way it is pretty good. Now this is the kind of Python code that we have used to calculate the theoretical and then experimental graph. So this is the reading what we have got, and we are drawing the graph. So green is what is theoretical, what we calculate through formula, and red is what we got. It is almost same. I mean, if we see at a particular time there is a gap of around 2 or 3. Okay, at one time they crosses each other, and then this is like so. Pretty well means I can say that the differentiation concept, what we are thinking, that if we know the area, differentiation of the area is the line equation. If I know the line, then area is its integration. So this is the concept that we prove if we know the formula. If we know the formula, then we differentiate the formula. Okay, like I is nothing but dq by dt, that is c dv by dt, and this is the theoretical equation of the I. Okay, so theoretical and practical are same. So this is the concept of differentiation, what we are saying. Okay, so we'll do animation again from the beginning slide. Okay, so initial is kind of what is addition, multiplication, integration. That is calculation of the area is the integration. What is relationship between integration and differentiation? Same thing, relationship between integration and differentiation. So one is addition and one is division. Now we go kind of further and we see the range by range, we calculate the area and we see the integration. And in the sine wave, we calculate the area and we come to a kind of integration solid concept, that integration is nothing but the area. And if we know the area, then calculating the differentiation is kind of getting back its equation. Now we go to lab section, and if we know the charge, then we calculate the current theoretically, and that current, theoretical current, that we verify through the practical sense, and then we see the kind of readings, and finally we see through a Python code that reading kind of corroborate it, it matches our expectation. So that is. So we saw the experiment result, like we started with a formula of calculating the voltage across the capacitor in the RC circuit. So in the RC circuit we have the capacitor, and voltage develops across capacitor slowly, and it reaches to a stage where it cannot go beyond it. So capacitor is fully charged. So if we know the voltage at any moment and we multiply with the capacitance, then actually we calculate the total charge that capacitor has stored at that moment. So if we consider the total charge as kind of integration, then differentiation would be dq by dt, and that is the current. So if we want to know the current at any moment in the capacitor, then we can find the kind of dq by dt, that is differentiation of the charge. So if charge storage area, if I have a current graph, means a graph which has current as the curve equation, then the area of the curve would be the char. So we tried to prove it experimentally, and first we have the theoretical voltage across the capacitance through which we derived the current across the capacitor through the differentiation. So voltage to charge and charge to current. So theoretically we have kind of every moment what would be the current as per the calculus differentiation. Practically also we saw that what would be the current. So practically there is no mathematics, we just saw the current at every moment. That current we match with the calculus differentiation what we achieved, and I think it is similar that's what we saw. So this corroborate means our experiment that if we have the area, if we know the area, then we can reverse way we can find out the line equation. Like if charge is the area, the line equation would be the current. If line equation is the current, integrating the current for a duration actually tells how much charge it is.